Quantitative literacy. This is the first video for 11.3. We're going to actually do problems 1A and B, and then we'll look at this idea of conditional probability. For number 1, we've got the numbers 1 through 10. That's our sample space. The event A is the number is odd. The event B is the number is a multiple of 3. So for the first problem, P of B, the probability of B, meaning what's the probability that the number is a multiple of 3? Well, the multiples of 3 in this set are the numbers 3, 6, and 9. That's 3 possible out of a total of 10. Excuse me, 3 numbers that are preferred out of a total of 10. So the probability of B is 3/10. For the next problem, the probability of A and B happening, that's saying that the number is odd and it's a multiple of 3. Well, if you think about it, the odd numbers in this set are 1, 3, 5, 7, and 9. Again, the multiples of 3 are 3, 6, and 9. Remember when we talked about this in the last unit, or actually, excuse me, in our first unit, and means both have to be satisfied. So I'm basically looking for the overlap here. 3 is an overlap, and 9 is an overlap. So to be odd and a multiple of 3, it's the numbers 3 or 9. So that's 2 preferred outcomes over a total possible of 10, or 1/5. Now, the next problems deal with this idea of conditional probability. So conditional probability is the probability of some event B given A. Basically what happens is, and here's how we write it with this little vertical line in the middle. The second event reduces my sample space down. And then I look at the first event. So even though this is originally saying 10 different things, 1 through 10, I'm going to reduce down that sample space and then pick from there. So let's see what this means. So on letter C, here's how you want to look at this. Look at the second letter. This is going to reduce my sample space down. Oops, I'm going to need more room than that. So A, the number is odd. That reduces my sample space to just the odd numbers. So now my total possible outcomes has no longer 10. It's now only 5 numbers. That's going to be the denominator of my fraction. Now, from that group, I ask myself, how many of those are multiples of 3? But again, it's only in this smaller set, 1, 2. So there are 2 out of a total of 5. Again, my denominator changed. So basically, if you think about this in words, it makes a little more sense. What is the probability that I find a multiple of 3 if I'm only allowed to look at the odd numbers, given that I'm only looking at the odds? There's a 2 out of 5 chance of that happening. So again, the second letter here is going to reduce down my sample space. So on the next problem, B, the number is a multiple of 3. Again, that's just the numbers 3, 6, and 9. So my sample space reduced to a total of 3 possibilities. So that's going to be my denominator. And now out of those 3, how many are odd? Well, 2 out of those 3 are odd. So the probability that the number is odd, given that it's a multiple of 3, there's a 2 out of 3 chance. So again, on conditional probability, it reduces down my sample space, basically saying it reduces down my denominator. my total possibles to look at. Similar concept on number 2. Given a family with 3 children, find each probability. We've done this problem before, but I'm going to write out the sample space again. This is the order they're born, so it could be boy, boy, boy. It could be boy, boy, girl. It could be boy, girl, boy. It could be boy, girl, girl. Okay, so there's all the boy leading. Now I'll do girl leading. It could go girl, girl, girl. It could go girl, girl, boy. It could go girl, boy, girl. Or it could go girl, boy, boy. There are 8 possible outcomes here. Those are all, each one of those scenarios is a possible outcome. So that's my original sample space. Now we've got this conditional stuff happening though. The oldest is a boy, given there is at least one boy. So again, this is going to reduce down my sample space. Basically, at least one boy gets rid of the girl, girl, girl possibility. So the sample space here is only 7 because the girl, girl, girl possibility goes away. And now, again, I'm not looking at that one. I'm not looking at the girl, girl, girl possibility. How many of what's left over has the oldest being a boy? Well, that would be basically the first 4. 1, 2, 3, 4. The first 4 possible outcomes. So there's a 4 out of 7 chance that the oldest would be a boy, given that at least one is a boy. For letter B, again, let's look at our given to reduce down our sample space, given that there are at least one boy and at least one girl. So this reduces my sample space down to, and I'll go ahead and just cross them out up here. Basically, there's got to be one boy and one girl at least. So that eliminates boy, 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 and girl, girl, girl. That leaves me with 6 possible outcomes. Now I look at the top part. The oldest is a boy and the youngest is a girl. Well, when does that happen? That happens there, and it happens there, where the oldest is a boy and the youngest is a girl, firstborn, lastborn. So there's 2 out of those 6, or a 1/3 chance of that happening. So conditional probability, we have to reduce down our sample space and then look at that smaller sample space for what we want. The other concept in this chapter is the multiplication rule. So if we have 2 events, the probability of both of those events happening, we multiply them together. Now, this second part here where it says probability of B given A basically means I have to look for overlap again, which we'll see in the problems. But the key concept here is that if I'm talking about 2 events happening, I multiply their probabilities together. Now, that being said, the first problem here is not a multiplication one. This is not an and, this is another conditional. So a little more practice with the conditional. Given that a diamond is dealt first, well, let's think about what that means. If a diamond is dealt first, that means there are now 12 diamonds left. What are the chances that I'll get another diamond? Well, there are 12 diamonds left. Now realize that I already dealt a card. Notice that it says without replacement, so I don't put the card back in. That means there's not 52 cards left, there's only 51 left. So after I've already dealt a diamond, there are 12 diamonds left out of a remaining 51 cards. Then you can reduce this, 3 goes into both, and you end up with a 4/17 chance. The next one, or the next several, are going to deal with this multiplication thing. We're going to figure out each one first. The first is a jack. Okay, the probability of a jack, there's 4 jacks out of 52, or I can reduce that to a 1 out of 13. The second is a face card. Okay, well, let's think about this. If I already gave you a jack, that is a face card. Normally there's 12 face cards, but if I dealt you a jack, now there's only 11 face cards. And remember, there was no replacement, so there were only 51 cards left in the deck. So the probability of the first being a jack was a 1 out of 13 chance. After I assume that that has happened, there are only 11 face cards left out of the 51 that are left in the deck. With the word and, I'm going to multiply these together. So it's a 1 out of 13 times multiplication, and 11 out of 51, which is 11 out of 663 chance. On letter C, the first is red, okay? The first is a red card. So there are 26 red cards, 13 diamonds, 13 hearts out of 52, which again, you can reduce to 1/2. The second is a club, okay? Remember, we've already dealt a red card, so there's only 51 in the deck. Well, if the first card was red, that did not influence the clubs because clubs are black. So there's still 13 clubs, but there were only 51 cards total. 13 out of 51 doesn't reduce, so it's a 1 out of 2 chance of getting a red, and then a 13 out of 51 chance of getting a club. I'm going to multiply those things together. And that gives me a 13 out of 102 chance. Again, multiple events, we multiply the probabilities together. For letter D, no face cards, okay? Well, think about what that means. That basically means the first card, card number 1, is not a face card. And number 2 is not a face card. So what are the chances that the first card you get is not a face card? Well, if there are 12 face cards, there are 40 not face cards out of 52, which does reduce to 10 out of 13. Now, assuming that I gave you a non-face card the first time, now there's only 39 non-face cards, and there are only 51 left in the deck. That can reduce as well to 13 over 17. I'm going to multiply these probabilities together, which actually you can cross-reduce a little bit. 13s can go away. And you're left with a 10 out of 17 chance. On number 4, 2 brothers each have 3 daughters and no sons. What's the probability of this event? Well, this is going to have several multiplications in it. Well, for the first brother, the first one being a daughter had a 1 out of 2 chance. The second one being a daughter, 1 out of 2 chance. The third one being a daughter, a 1 out of 2 chance. So that covers the first brother. And the second brother had a 1 out of 2 chance of a girl, a 1 out of 2 chance for a girl, a 1 out of 2 chance for a girl. So really, I'm basically saying, what are the chances of having 6 girls, no boys across the board? Multiple events, I multiply these probabilities across the top. All the ones multiplied would just be 1. On the bottom, 2 times itself 6 times, 64. So that event had a 1 out of 64 chance of happening. All right, we'll do a different video for the second part of this.